In a modern war, the first shot may never be heard. No missile launch, no tanks crossing borders, no air raid sirens, no dramatic declaration on live television, just a phone call between capitals, a regulatory notice published online, a shipment delayed at a port, and suddenly the future begins to slow down. Factories pause, engineers wait, markets react, governments panic. For most of the last century, power meant oil fields, aircraft carriers, steel mills, nuclear weapons, and armies large enough to occupy continents. But in the 21st century, power increasingly hides in silence. It sits inside smartphones, satellites, data centers, hospitals, fighter jets, missile systems, and artificial intelligence models. It powers Wall Street transactions, military logistics, medical research, and the digital lives of billions. That power has a name, the semiconductor. But here is the real mystery. Why does one relatively small Dutch company hold a choke point over the global future? Why has the United States treated chip technology as a national security weapon against China? Why is Taiwan now one of the most dangerous places on Earth because of factories few people have ever seen? And if America leads today, can that dominance actually survive the next decade? By the end of this dossier, those questions will be answered. Because the most important contest on Earth is not being fought in trenches, oceans, or skies. It is being fought inside sterile clean rooms, precision laboratories, and machines capable of carving invisible circuits onto silicon with near-atomic accuracy. The question is no longer whether the United States and China are competing. The question is who will control the brain of civilization. To understand how the world arrived here, we need to go back decades. In the 1980s, the United States still represented overwhelming technological strength. American companies led in aerospace, computing, software, finance, telecommunications, and semiconductor innovation. Silicon Valley was emerging as the engine room of modern capitalism. American universities attracted global talent. The US dollar anchored global finance. Washington entered the post-Cold War era with enormous confidence. At the same time, globalization accelerated. Corporations searched for lower labor costs, larger production networks, lighter regulation, and access to expanding consumer markets. During the 1990s and 2000s, industrial capacity shifted toward Asia. China became the center of gravity. It offered labor scale, infrastructure growth, export discipline, political stability, and state-backed industrial coordination. Factories multiplied, ports expanded, high-speed rail lines appeared. Entire cities rose in a single generation. Supply chains that once crossed American states now crossed oceans. In return, Western economies gained cheaper goods, stronger margins, lower inflation, and rising shareholder returns. Consumers benefited. Investors benefited. Multinational corporations benefited. Many in Washington believed this arrangement would eventually liberalize China. The theory was straightforward: integrate Beijing into global markets, expose it to private enterprise, expand prosperity, and political openness would follow. But history moved in another direction. China used global integration not to become a copy of the West, but to strengthen itself on its own terms. It absorbed manufacturing know-how, trained millions of engineers, expanded supply chain depth, invested in strategic sectors, and climbed steadily up the industrial ladder. What began with textiles and toys moved into electronics, telecom systems, batteries, solar equipment, industrial machinery, electric vehicles, shipbuilding, robotics, and advanced computing. The result was one of the fastest industrial transformations in modern history. Hundreds of millions rose out of poverty. China became central to global trade. It accumulated capital, influence, and production capacity at a scale rarely seen before. Yet one critical weakness remained. China manufactured much of the body of the world economy, but not all of its brain. That brain is the semiconductor. Chips are often described as components. That dramatically understates their importance. Semiconductors are the control layer of modern civilization. They regulate energy inside vehicles. They process medical scans in hospitals They guide aircraft navigation. They secure communications networks. They power industrial robots. They enable precision weapons. They train artificial intelligence. They run cloud computing. They optimize logistics chains. They support financial systems moving trillions of dollars. Remove advanced chips from a modern economy, and decline does not arrive overnight. It arrives gradually. Productivity slows. Innovation stalls. Defense systems age. Infrastructure becomes harder to upgrade. Competitors move faster. Strategic dependence deepens. Not all chips are equal. Mature chips remain essential and power appliances, industrial systems, and automobiles. But leading-edge chips deliver greater speed, lower power consumption, smaller size, and higher efficiency. Those advantages multiply across entire economies. Faster processors improve defense simulations. Better GPUs accelerate AI training. More efficient chips strengthen data centers. Smaller nodes enable more powerful mobile devices. That is why semiconductor leadership is not just an economic issue. It is a civilizational advantage. The global chip supply chain is one of the most sophisticated production systems ever created. Chip design remains heavily concentrated in the United States. Advanced fabrication capacity is centered in Taiwan and South Korea. Critical equipment comes from Europe and Japan. Precision materials come from a small group of trusted suppliers. Software tools are controlled by elite firms with decades of expertise. No single nation controls every stage. That model created extraordinary efficiency, but it also created extraordinary vulnerability. When only a few companies dominate key links, those links become geopolitical choke points. A software license can matter as much as a naval base. A machine tool can matter as much as a missile battery. A supplier contract can matter as much as a treaty. No choke point is more important than lithography. Lithography is the process used to project circuit patterns onto silicon wafers. It is how modern chips are born. And at the most advanced level of that process, one company became dominant, ASML. Based in the Netherlands, ASML became the only company on Earth capable of mass-producing the most advanced extreme ultraviolet lithography systems, known as EUV machines. These machines are among the most complex industrial tools ever built. Each system contains tens of thousands of components. It uses lasers striking microscopic droplets of tin to generate plasma hot enough to emit EUV light. That light is then guided through mirrors, polished to astonishing precision. The process happens inside vacuum environments because EUV light is absorbed by air. Even tiny instability can ruin production. This is not ordinary manufacturing. It is industrial physics operating at the edge of what is commercially possible. So why does this matter geopolitically? Because if only one company can reliably supply the machines needed for the most advanced chips, then everyone else must adapt around that reality. Washington understood this. As strategic competition with Beijing intensified, American policy shifted. Technology would no longer be treated as a neutral byproduct of globalization. It would be defended as an instrument of national power. In 2022, the United States expanded export controls targeting China's access to advanced chips, chip-making tools, and selected technical support. The stated rationale focused on national security and military use concerns. But the broader signal was unmistakable. America was willing to use technological leverage directly. Those decisions mattered because modern chip production depends on a web of allied suppliers. The United States influences design software, key intellectual property, top-tier chips, and diplomatic coordination. Europe provides essential equipment. Japan contributes materials and tools. South Korea and Taiwan contribute manufacturing strength. Strategic alignment among these actors magnifies American leverage. One of the least understood factors in this competition is human capital. Semiconductor leadership does not rely only on hardware. It depends on engineering culture, yield management, troubleshooting experience, process discipline, and thousands of highly specialized experts. You cannot instantly replicate decades of accumulated know-how simply by funding new buildings. That is why time matters so much. Delays in yield improvement, packaging capability, process refinement, or supplier reliability can cost billions and postpone entire technology generations. This did not end China's ambitions. Claims of instant collapse were exaggerated, but restrictions did raise costs, increase uncertainty, complicate procurement, and slow access to frontier capability. At the same time, the United States moved to strengthen domestic resilience. The CHIPS Act signaled the return of industrial policy on a scale few expected in modern America. Subsidies, tax incentives, workforce investment, research support, and new fabrication plants became part of a national strategy to rebuild critical capacity. Companies such as Intel sought to restore manufacturing leadership. New projects were announced in states such as Arizona and Ohio. Universities expanded engineering programs. Governors competed for investment. Semiconductor policy, once obscure and technical, became mainstream national strategy. At the center of the map stands Taiwan. Through TSMC, Taiwan became home to the most advanced contract chip manufacturing capacity in the world. That success created wealth, but also strategic danger. For the United States, stability in the Taiwan Strait became economically vital. For China, dependence on an island politically separate and strategically aligned with Washington represents an unacceptable vulnerability. For the global economy, any disruption there would trigger immediate shortages across electronics, automotive manufacturing, cloud infrastructure, and defense systems. That is why Taiwan is not simply a regional issue, it is a semiconductor issue with global consequences. Yet narratives of inevitable Chinese failure ignore major realities. Beijing did not remain passive. China responded with state-backed investment, domestic substitution efforts, talent development, research incentives, and long-term industrial planning. Chinese firms advanced in batteries, electric vehicles, telecom hardware, drones, mature node chips, renewable energy systems, and applied AI. China may still face barriers at the most advanced frontier, but scale matters. Domestic demand matters. Persistence matters. Nations with large internal markets can sustain industries through long development cycles. Nations with centralized coordination can direct resources quickly. These strengths do not guarantee victory, but dismissing them would be a strategic mistake. The next decisive battlefield is artificial intelligence. Advanced AI systems require compute power, specialized accelerators, vast data sets, elite researchers, abundant electricity, and software ecosystems capable of rapid iteration. US restrictions on top-tier GPUs aim to slow China's progress in training frontier models. But AI capability does not depend only on one chip generation. Efficient code, custom accelerators, distributed computing, domain-specific models, and model compression can narrow gaps over time. That means controls may delay leadership races without permanently ending competition. Meanwhile, America retains enormous structural advantages. The United States leads in research universities, venture capital depth, cloud infrastructure, startup culture, software ecosystems, frontier laboratories, military R&D, and reserve currency power. It also benefits from alliance networks across Europe and Asia. When coordinated effectively, those networks amplify US leverage far beyond its borders. But leverage has limits. If restrictions are overused, rivals accelerate self-sufficiency. Markets fragment. Global firms lose revenue needed for future innovation. Neutral countries hedge, supply chains split, political pressure grows. This raises the largest long-term risk of all: technological bifurcation. Imagine two partially separate systems, one centered on American standards, chips, cloud services, software rules, and security architecture. Another centered on Chinese platforms, industrial financing, telecom networks, and digital ecosystems. Different chips, different operating systems, different standards, different trust models. Such a split would likely increase costs, reduce efficiency, and slow some forms of innovation. Redundancy can improve resilience, but duplication consumes capital. Scientific cooperation could weaken. Businesses would face heavier compliance burdens. Smaller nations would feel pressure to choose sides. So, has the United States already won? Not yet. What Washington has done is something more subtle and perhaps more powerful. It has demonstrated that in the modern era, controlling choke points can shape the strategic environment without firing a shot. China, in response, has turned self-reliance into national doctrine. It understands that dependence in critical technologies creates vulnerability. Whether Beijing can close key gaps remains uncertain, but its determination to try is beyond doubt. The 21st century may therefore be decided less by battlefield victories and more by industrial endurance. Who can build faster? Who can scale production reliably? Who can secure energy and talent? Who can finance research during recessions? Who can innovate under pressure? Who can absorb shocks and keep learning? Everyday life already reflects this struggle. When you unlock a phone, stream media, use GPS, receive medical diagnostics, or transfer money online, you interact with systems shaped by semiconductor competition. The technology war is not a future scenario. It is the present condition of global power. The coming decades may be remembered not for armies that marched across borders, but for factories that stayed online, laboratories that innovated faster, and nations that converted knowledge into durable strength. The chip is tiny, nearly invisible, yet an increasing share of humanity's future rests inside it, and that is the real lesson of this era. Power no longer depends only on territory or population. It depends on who can organize talent, capital, energy, materials and ideas into machines small enough to disappear from sight, yet powerful enough to shape the world. Dossier closed.